Good afternoon, dear friends, dear students. Today we are going to discuss about the methods of elimination of spherical aberration. What is spherical aberration? It is a defect in the image. The image is formed in the form of a sphere, even though it is a point object. Its image is extended laterally as well as longitudinally along the principal axis. This is because of the size and thickness of the lens. So to eliminate this problem in the image, there are some methods. The first one is by making use of stops. So this problem arrived only because of the size of the lens. Suppose if we keep a stop, I don't think here we are having it. So a stop is a small opening. A stop is like a small opening. If we keep that a small opening, a small disc-like one, it will have opening at the center in the form of a circle, and the remaining part is opaque. So it allows only a portion of the light rays onto the lens. So it allows either the paraxial rays or the marginal rays only. So by this, we get image only because of either by marginal rays or by the paraxial rays. Of course, the elimination of spherical aberration is done by using a stop, but the brightness of the image will be very less because the brightness of the image depends upon the number of light rays that are forming the image. Since we are using stop here, the number of light rays that are incident on the convex lens or the concave lens, whatever the lens may be, are very less. So here the aberration, spherical aberration is eliminated, but the brightness of the image will be less. The image may not be clear. And the second one is by using two suitable lenses in contact. You already know in the case of chromatic aberration, here two lenses are kept in contact. One is convex lens and the other one is concave lens. The other one is plano-concave lens. This is made of crown glass and this is made of flint glass. Likewise, to eliminate the spherical aberration, a combination of two lenses that are kept in contact each other is used. Here, it was arrived that if the ratio of focal lengths of the two lenses that are in combination or that are in contact is minus 1 by 6. If the ratio of if the ratio of the focal lengths of the combination is minus 1 by 6, then that lens may be used for the elimination of spherical aberration. Such a lens is called as crossed lens. So by using a crossed lens, we can eliminate spherical aberration. Okay. The other one, of course, I told you about this crossed lens. Okay, the other method is by using two plano-convex lenses separated by a distance. See here, these are two plano-convex lenses of focal lengths f1 and f2. If the first convex lens, the first plano-convex lens is alone is used and the object is at infinity, this ray which is parallel to the principal axis indicates that the object is at infinity. So if the only convex lens is used, then the image will be formed at this point. Let us say another plano-convex lens is also used, separated by a distance d. Now, this again bends the light rays that are incident on it, and the final image will be formed at f1. Okay. Now, you all know, excuse me, if v is the distance of the image and u is the distance of the object, then 1 by v minus 1 by u is equal to 1 by f2. In this, u, that is the distance of the object, is f1 minus d. This is d and this is f1. So, this is f1 and this is d. So, the distance of the object is f1 minus d, and the distance of the image is f1 minus d by 2. Okay, from this we get d is equal to f1 minus f2. Of course, there is some other derivation by making use of the similar triangles. We will know it in the through your notes. Okay, it is not explained here. So if the distance between these two plano-convex lenses is the difference of the focal lengths of these two convex lenses, that is f1 minus f2, then the spherical aberration will be eliminated or minimized. This is another method of eliminating the spherical aberration. Next, the next problem in the images, in the formation of images, that is coma. Here, see the image, this one, yeah, this one. Here, this problem is arrived because when the point object is just nearer to the principal axis, it is not lying on the principal axis, but it is nearer to the principal axis. So, if a point object at O is like is here, the cone of rays that are incident on the convex lens are brought to focus at various positions. See here, the paraxial rays, here it is denoted by the number 1, 1, 1. The paraxial rays, which are nearer to the principal axis, that is 1, 1 ray, it is brought to focus at this point. The ray which is undeviated, it is brought to focus at this point. The ray which travels through the center of the lens will pass through the lens without any deviation. So, it will form the image at P. Suppose, let us suppose a screen XY is kept here. So, on the screen, we find the image at P by the undeviated ray. Whereas, by the rays 2 and 2, see here, what is 2? The ray that is incident on the convex lens at a height from the principal axis, likewise at a height below the principal axis. If these two are same, that means the rays that are incident with the same inclination or with the same angle are at the same height. This distance is same as this distance. So, the rays that are incident at equal heights, they come to a focus which is at another place. See, the 2 rays are brought to focus here, whereas the 3 rays are brought to focus at some other point, that is at R. And the rays 4, they come to focus at this point S. Now these rays are diverging from this point, and the 3 rays are diverging from this point R. So if we keep the screen here, we find the images due to 2 rays, 3 rays, and 4 rays like small discs. The sizes of the discs increases as we go perpendicular to the principal axis and towards the principal axis. That means the magnification increases. So these images overlap, and finally the image will appear like a comet. See here, it is having a tail like, and this is head. So this appears like a comet. That's why this defect in the image is called as coma. Okay, this is all about the explanation I already made to you. And what are the methods of reduction or elimination of coma? So for every monochromatic aberration, a common elimination method is present, that is making use of stops. If we use a stop at a suitable distance from the lens, it cuts other rays. Suppose if a stop is used here, it allows only these rays and it eliminates all these rays. These 3, 4 rays will be eliminated if we keep a stop here. It allows only 1 and 2 rays, this portion of rays only. So the images cannot be formed by those rays that are far away from the principal axis. Of course, again, the image will be formed here, but the brightness will be very less. The image may not be clear because less number of light rays are forming the image. So, of course, it is an elimination method using of stops, but it gives some other problem in the image that reduces the brightness of the image. Okay, and the the coma is positive for convex lens and negative for concave lens. So by making use of the combination of two lenses, convex and concave lenses, and keeping them in contact, the problem that is coma may be eliminated. And here we use a condition that is mu1 by 1 sine theta 1 is equal to mu2 by 2 sine theta 2. This is called as Abbe condition. Abbe is the name of a German optician. He is a scientist. So he arrived this relation, that is mu1 by 1 sine theta 1 is equal to mu2 by 2 sine theta 2. If this condition is fulfilled or is satisfied, then the image will be formed with free from the defect coma. Here mu1 is the refractive index in the object environment, is the refractive index in which the object is placed. Usually we place the object in air in front of a lens. So here mu1 is the refractive index of the medium in which the object is placed. Usually the refractive index of air is taken as 1. And y1 is the size of the object. This y1 is the size or the distance of the point object placed at which height from the principal axis. Excuse me. See, this y1 is the height of the image, height of the object at which the object is placed from the principal axis. And theta 1 is the angle made by the incident rays. See here, these rays, this ray 1 is making an angle, certain angle at the convex lens. Likewise, these rays, all these rays are making a certain angle with the convex lens. So these are the incident rays. Those are making a certain angle with the principal axis of this convex lens. Yeah. So mu1 is the refractive index of the medium in which the object is placed. Y1 is the height of the object from the principal axis, and theta1 is the angle of incidence of the incident rays on the convex lens. Whereas mu2 is the refractive index of the medium in which the image is formed. Usually the image also forms in the air. We keep the object in air, excuse me, we keep the object in air and the image will be formed in air usually. So if the image is formed in air itself, then mu1 is equal to mu2 is equal to 1, because the relative refractive index of air is 1. And y2 is the height of the image from the principal axis, and theta 2 is the angle made by the refracted rays. The refracted rays form the image. These are the refracted rays, and the image is formed by these rays. And if the condition, Ebb's condition, that is mu1 by 1 sin theta 1 is equal to mu2 by 2 sin theta 2 is obeyed, then that lens forms the image free from coma. Okay, so this is about coma. And next to this, we have some other monochromatic aberration, that is astigmatism. Here, this problem, that means the image will be formed, of course, the object is a point object, and the image will be formed along two straight lines which are mutually perpendicular to each other and separated by a distance. See here, the object is at B, it is a point object, and it is placed far away from the principal axis. Now, the rays that are incident on the convex lens, of course, this is a very thick convex lens, and the plane of rays may be separated in two mutually perpendicular distances, mutually perpendicular directions. See, along RS, this is a plane called as sagittal plane, and the plane along MN, it is called as meridian plane. The rays that are incident on the convex lens in the sagittal plane, they come to a focus far away from the convex lens, that is at P2. Because of these sagittal rays, the images will be formed along the straight line. So P2 is the image of this point object, which is perpendicular to the principal axis. Again, there is another plane which is called as meridian plane, and the light rays that are incident, the light rays that are incident in the meridian plane, they come to a focus at a lesser distance, that is at P1. Now again, because of the meridian rays, the point images will be formed along straight line P1. This line will be parallel to the principal axis. So, the image of the object at B, the images of the object at B are formed in two mutually perpendicular lines, that is along P1 and along P2. Again, if we keep a screen at P2, And if we move the screen towards P1, then at a particular position of the screen, that is where the sagittal and meridional rays meet, an image of less astigmatic problem will be formed. The thickness of the disc, the image will be formed in the form of a disc. The thickness of the disc or the diameter of the disc will be minimum at this position of the screen. Now, this position is called as least distance of distinct vision, as we told in the case of spherical aberration. Whereas the screen is moved along the principal axis here. Let me show. Of course, it's not displayed. I hope it was displayed. Yeah, we will get it here. Yeah. This is the point where the paraxial rays meet, and this is the point where the marginal rays meet. Now the image will be formed in between these 2 points, and the image looks like a spheroid. If the screen is moved from this point to this point, we came to know that at this position of the screen, the image will be formed in the form of a disk of uniform intensity. This is called as least distance of distinct vision. This is along the principal axis, whereas in the case of excuse me, whereas in the case of coma, astigmatism, it is not along the principal axis. It is in some other direction that is along the meridional and sagittal planes. So if we observe the images will be formed like this. At P2 it is along a straight line, and at P1 it is again along a straight line. These 2 lines are mutually perpendicular to each other. In between these 2 points, the image will be formed like this. Whereas at the point where the meridional and sagittal rays meet, the image will be formed in the form of uniform circular disc. So that this position is called as least distance of distinct vision. So this is about spherical aberration. Again, the elimination methods for spherical aberration are again the elimination methods of coma. We all know the common method for the monochromatic aberration is the elimination of monochromatic aberration is by making use of stops. So again, if we use a stop here at a suitable distance, and at a suitable distance, we can eliminate one of the images that are formed in the image environment. So if a stop is used and the meridional rays are eliminated, the image will be formed only by sagittal rays, and the image will be formed at this P2. And if the sagittal rays are eliminated by using the meridional rays, then the sagittal rays, then the image will be formed only at P2. And if we use the meridional rays, the image will be formed only at P1. So in this way, we can eliminate So in this way, we can eliminate the astigmatic problem by the lens. And by making use of the suitable convex and concave lenses in contact, the problem may be reduced. Here, astigmatism for convex lens is positive and astigmatism for concave lens is negative. So by combining these two rays, by combining these two lenses, the astigmatic problem may be reduced. Okay. So the next problem, that is curvature of field. See here, in the previous cases, spherical aberration, comma, and astigmatism, the object is taken as a point object. Whereas in this case, the object is a linear object. It is extended from A to B. Such an object is placed in front of a lens, then the rays that are incident and the rays that are refracted from the center of the lens, see here, these are the rays from the center of the lens, and we can consider these rays as the paraxial rays. So these two are brought to a focus at this point B dash and at this point A dash. Okay. Whereas the rays that are incident at the margin of the lens, they come to another focus. So because of the marginal as well as the paraxial rays that are emitting from the linear object, they come to various foci, that is from A dash to B dash. Along the principal axis, they come to focus here, whereas at the point A dash, they come to focus here. Likewise, they come to a focus at B dash here. So of course, the object is a linear object. It is along a straight line, but its image is curved. If the object is placed in between the principal focus and the optic center of the lens, by means of this convex lens, we can get a virtual image on the same side of the object. So in the second case, see here, the object is placed here and its image is formed at this point, at this plane, that is A dash B dash. Again, it is curved like. So it appears like a curved image. So this also can be reduced by getting back, I think. So these are also the object is linear and the image is curved. Okay. So to eliminate this problem, we take the radius of curvature of the convex lens as sigma 1 by mu n Fn. Here, R is the radius of curvature of the effective convex lens that is formed by the combination of various convex lenses with refractive index mu and focal length f. If mu1 is the refractive index and f1 is the focal length of a lens, such lenses with various other refractive indices and focal lengths are used as a combination, then if the radius of curvature of the combined or the lens that is formed in the combination, then if this condition is satisfied or fulfilled, that is 1 by r is equal to sigma 1 by mu n fn, if n number of lenses are used in the combination, then okay, then if we follow the condition, that is, if the image to be flat, that means flat like the object and not to be curved, the radius of curvature must be at infinity. Here the radius of curvature of the combination of lenses r must be at infinity. So r to be at infinity, if we substitute the value of r infinity, then 1 by infinity is 0. Then sigma 1 by mu n fn, it becomes 0. So if such condition is fulfilled, then the problem, that is curvature of the field, may be eliminated. Okay. The next problem in the formation of images is distortion. Here we use an object which is like a mesh. It is like a rectangle or a square. Now various rays that are incident on the convex lens, they come to a focus at various points. So if you take a point on the object, it will be come to a focus, of course, at here like that. And if another point is taken, it will be come to a focus at some other point, and they are looking like diverged. Then the image will be appeared like a barrel. In some other cases, the image will be look like a pin cushion. These two are the defects in the image. Of course, the object is a square-like, but the images are like either a barrel or like a pin cushion. So this is a problem in the formation of image. This problem is called as distortion. See here, this is one of the methods to eliminate the problem, that is distortion. Here, two convex, concave, combined lenses are separated by distance, and a stop is placed in between these two lenses. Then the image will be formed like the object. Okay, this is the elimination method for the distortion. Okay, so with this we conclude the first unit, that is aberrations. Of course, I should explain this subject in Telugu also. I don't think we have much time. So in less than 1 minute, our time is going to close. So I will explain this subject in the next class in Telugu also. Telugu medium people, don't worry. Okay, we'll meet again in the next class. I think it is closed. The time is completed. Okay, bye.